Outstanding. That was marvelous. Just 1 second here. I'm just trying to get see where are you? Hello. I do love to hear about your love life. I am very excited that you have news. Let's see. I'm guessing. All right. We'll throw it out there. I'm gonna guess that you went on follow-up date number 2. Oh no, because you were inviting them over, right? Was that it? Thank you, Potato. So, I hope things went well. I hope things went very well. Very cool. Exciting. I'm getting beautiful, wonderful. That's amazing. Congratulations. Oh, that's awesome. Dude, that's so cool. I love seeing it when, when people do things, and especially like this, and they're happy. They make themselves happy, and they make other people happy, and that's just wonderful. So I am so glad. That is so awesome. Speaking of making people happy, dog, do not chew on any cables. That will make neither of us happy. Yeah. Weapons. Okay. Ah, wonderful. Well, I, for one, am glad that we could be here to hear about your successes. That's wonderful. That's amazing. Oh, Tato, buddy, doggo, 4-pawed love of my life. Please do not pull the books off the shelves. I haven't even had the chance to really get started. Yesterday. It was yesterday. I've got my eye on you, Potato. Yeah, go outside. Yeah, there was someone on a bike. You should go ruin them. Yep, yesterday was my birthday. I was old, am still older. Am now older. Whatever you want to say. Yes. Yes, indeed it was. But, yeah, so I went, I had a time with, just went over to my friend's house and, hung out with them for a little bit, and then came home to the dog, and then I just absolutely crashed by accident on the couch. I fell asleep. I'd been planning to do like a stream or something. It didn't happen. It did not happen at all. I accidentally fell asleep. Woke up like in the middle of the night, like, huh? What happened? Oh no. Well, I guess we're going back to sleep now. Well, thank you so much, Utensil. I really appreciate it. And yeah, it was pretty good. Low key, but that's really all I wanted. So yeah. Okay, so Potato is trying to entertain himself, but I fear that he will get to the end of his ability to do so pretty quickly. Yep, there he is. I'll be right back. Potato! Potato! Oh, do you want me to put a nom in there? All right. I'll be right back. I'm just gonna put a little treat in his little roller toy thing. So I will be right back, and then we'll get started. But thank you very much, Utensil, by the way. Thank you. I appreciate it. I'll be right back. Oh, let me put up something like a yeah, good enough. Not actually making tea, but you get the point. Hi, Potato. Would you like it if we put something in here instead of going after my books? That would be wonderful, right? Okie dokie, and we're back. We're back. So that means we can take this. Nope, not that one. This off. There we go. Beautiful. He would absolutely just like lay on a couch with people waving palm fronds over him as he eats snacks. That is 100% in his job description. He would take that in a heartbeat. He really is a very good dog, but sometimes, man, sometimes. Oh, I didn't even. I'm so verschmiggled. Didn't even set up my my little tablet here to take, so I could actually take notes on what's going on. So things might go a little wonky for a second here. Oh no, pretty good. They're pretty good. Okay, cool. So I decided that we would go back to some of this more ridiculous math that we were doing last time. Yeah, so let's dive a little bit back into what we were talking about. All right, so we're talking about kind of the general background quantum mechanical theory that is underlaying the Feynman path integral stuff, right? And how we get there. And we talked about, I'm just going to erase those things are a little more visible. We talked about the time-dependent Schrodinger equation, right? This is the classic time-dependent equation. We've got our kinetic energy. We have our potential. Then we have our what's it called? Our wave function that's representing a particle or a system, right? And that's, of course, a function of position and time, which is why it's time-dependent, right? So you see this derivative with respect to time. So this is when you have a derivative with respect to a certain variable, it's asking how is the function changing if I change that variable, right? So that's what it's asking. So it's asking how is psi changing with respect to time compared to how it's moving around with the energy, right? So how does that time evolve? And the goal was to get something called the propagator, right? And so the propagator is supposed to answer this question, right? So this is the equation. This isn't the solution to the equation, right? This is the equation that you use to get there, right? It's a differential equation. And so from there, we wanted to get the propagator that's going to actually allow us to solve this under more than just very well, it's still going to be under very specific circumstances, but ideally that's what you want, right? You'd like to be able to find some sort of way to generally solve these things under different conditions that you would see in real life. Never actually happens because these solutions end up being very difficult. So you end up with a couple of kind of toy examples like the harmonic oscillator, the free particle that's moving independently of any sort of influencing fields, these sorts of things. And then you sort of perturb off from there and say, all right, I'm close to this, but kind of not. So how does it change with that, that kind of thing. So that's what we had been talking about. And of course, the two big pieces we had were the Hamiltonian, and even in classical mechanics, you get this. There's the Hamiltonian, which again is the kinetic plus the potential energy, and then there's the Lagrangian, which is the kinetic minus the potential energy. Right. And so we have this operator, e to the negative I t h over h bar describes the time evolution of some state, right? So we say we don't necessarily know exactly what state psi is in. It's probably in a sum of different states at the same time, right? It's in this superposition, this multiple states, but it's changing over time, right? The proportion of it that's in one state versus proportion in the other state, the probability that's going to be one versus the other is going to change over time. And so this is kind of this operator here, which is taking that Hamiltonian, which again is the kinetic plus the potential energy. And if you notice, it's in the exponential here. It sort of tells you how the states evolve over time, right? So H is the generator of U, right? So the Hamiltonian's the thing that gives you this operator U. And we said the time evolution for some state psi reads this psi, the double derivative with respect to time, right? Is that no? He had weird notation here. One second. Thinking. It was like single prime was initial position and double prime was final position or something silly like that. Okay. Blah 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 blah. Where KT. I believe that's what it was. Right? Because there's a final position. Yeah. So for some unknown reason that's you never see anywhere else, or it's probably standard within some community, but I've never seen it. The single prime is in the initial position / initial time, and the double prime is final, right? So it's going from position Q prime to position Q double prime at going from T prime to T double prime. I don't know why he's using this instead of initial and final, but whatever. That's all we need to know. So what we're saying is that our wave function, right, the state, the wave function state at the final time is equal to this unitary operator that's a function of both the initial and the final times your initial time, right? So in other words, what are you doing? You're taking your initial time, you're multiplying it by this operator, and you're getting the state at the final time, right? So that's telling you how the operator or how the wave function is evolving over time. That's what U is giving you. Rewriting the time evolution with UT as an integral operator, which is it's another means of describing it. You could describe it either as a matrix operator or as an integral operator. These are interchangeable, but excuse me. Right. Rewriting the time evolution, right, as an integral operator, we've got, so if we remember looking at what was going on last time, right, so psi at the final position, final time. All right, and there's our psi at the initial position, initial time, right? So we're going from here to here. That's the whole point of this. We're integrating. Here is our kernel. And this is G. Okay, and this is kind of the right. This is telling you how the space itself is shaped, right? So this is telling you how it's evolving in the space, and this is telling you what the space looks like that it's evolving in, right? And the combination of kind of those changes are what give you the final state, psi q double prime t double prime, where KT is a celebrated Feynman kernel. Right. So this, on the other hand, proves that KT is indeed the correct. Okay, all right, sure. So let's just hop down to here. H time independent. We have. No, I think we have to go back. Hold on. Where KT is a separated Feynman kernel, having explicit expression for KT in 1.3, one can derive the time or derive the limit t as epsilon approaches 0 equation. This, on the other hand, proves that KT is indeed the correct integral kernel. Okay, sure. Rigorous proof is something we don't have to worry about. So something that we know, if we want to figure out what's happening, like time 1 to time 2 to time 3, it's the same thing as time 1 to time 3 with this propagator, right? So if we just make time 1 to time 3 versus time 1 to time 2 to time 3, right? Cool. So H is H time independent. We have K. So again, this is our kernel operator that we've met, or the kernel, the Feynman kernel. So that's what's going to go into here. Is, let me see, for Q double prime, Q prime, and T double prime plus D prime. That's an interesting. Okay, right, because that's the amount you've traveled in that time, right? Hold on one sec. Q. Okay, you're doing kind of change in variables kind of thing. Yeah, you're doing kind of a transformation thing, right? Where you're going from Q to Q prime, right? And from T to T prime. So it's just telling you how these sort of come together. All right. In the case of Euclidean space, we're the GAB, so that's the metric, is a delta function. S is just the classical action, which we had said before. So then S equals the integral of your kinetic minus your potential over all time, right? Which of course is the integral of the Lagrangian over time. And then we get explicitly Euclidean Right. We had talked about this. This was the step functions, right? So what you're doing is you're breaking up your movement. Oops, they're a little bit off here. You're kind of breaking things down into these series of end divisions, right? And then you say, well, it's evolving in a certain way at this delta t, right? And then so here's our initial and here's our final. And what you do is you increase, if you were to integrate this, right, you're essentially increasing the number of these steps. So each step is smaller. So it goes like, dook, 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 right? And so as this approaches an infinitesimal, that's what you get the integral of it. And then, right, as the number of steps approaches infinity, d is dimension Euclidean space, we get, this is our kernel, right? This is what we need to put into here. In the end, what we're trying to do, right, is we're trying to get this. We want to know our state at the final position, final time. And we know if we integrate it, our initial position, initial time that we know, times this kernel, times our metric, that'll give us our final, right? So that's the answer we want to get. So we have to figure out what this k is, and this is what this whole shenanigans is going about, is trying to find what the heck this k function is that will get you that integral. So as we walk back through this again really quickly, right, we can look at this again. So what is our k function? Well, it's taking our to q. Hold on one sec. T to q. So limit as n approaches infinity, right? So there's our number of steps. And we are just multiplying the result of each of these together. And we're integrating exponential. I over h bar is just a constant. And it's the sum of these individual components, right? These individual steps. And this is our Lagrangian, right? So we're integrating our Lagrangian, which again is the action. We said that's the definition of the action S, right? So we are, for each of these, we are integrating to get the entire action, right? So what we end up with is, because the integral can go inside or outside the sum, so you can have the sum of the exponential of I over h bar times S sub j, right? J equals 1 to n, and then we're multiplying those all together, right? J equals 1 to n minus 1, right? So if you notice, what we've done here is we've said, because again, you can move this integral inside the sum. So we're integrating our Lagrangian to get ourselves our action, which again, just is, yep. So that's the definition of it. And then we're just kind of adding them together and multiplying them. And so that's what it's doing. Okay. And this is defined as, so this operation is defined as dq, capital DQ. Let's see, q of t initial. Okay, so from q initial to q final, right? So if you notice, we've changed our variables from qj, right? So from the j dimension of q, we're just saying now, or the j step, right? So each of these is a different step, each of these q's or each of these j's. Instead, we say no. We're switching around what we're integrating, right? And we're going from our initial position to our final position, and now our integral becomes an integral over time instead of an integral over the specific step that you're talking about, right? So it's just a change of variable. Nothing else has changed here. So we change the variables around to being from an integral of q sub or qj, right? The jth q, dimension q, to time, and then we just throw this label down and we say this is what we mean. Right? That's what the capital D is defined as. Is this shenanigans? Let's see what's actually enclosed in the capital D. Our what's it called? Product. Our big product and our big sum are kind of enclosed in it. And some of these are switched out from the variable change too, so I don't know 100%. Okay. Alrighty. I need a drink. Whew. My voice has mostly come back. Yeah. Oh, I need to also do this so it's a little more visible as to what the heck is going on. There we go. So again, as we go through this, right, and this I really want to foot stomp this. As we go through this, it's okay if we don't understand what's going on 100%, right? Again, the goal for each time is to get a little bit more knowledge, get a little more familiar with what's going on, so that each time we chip away at the overall puzzle. So it's okay if we don't catch everything. We're not, or at least I'm not going to catch everything. You might catch everything. I'm not. But yeah, this is sort of the constructive process of going through this. Man. Oh. Hold on one second. I just want to check one thing. You'll excuse me for one moment. There we are. Beautiful. All right, we got here, we got that going, we got that. Okay. Potato is enjoying his little treat somewhere downstairs. The fact that he hasn't come upstairs and the fact that the downstairs is quiet is vaguely concerning, but you know. Right. So what are the practical uses of this? Well, I'm trying to I have a particle that's in a certain state, right? So maybe it's an electron in an electron shell, right? It's in a certain state. And I want to know what are the chances it bounces to this lower shell and releases a particle or releases a photon, or I have a set of quantum bits that I've entangled, and I kind of want to know what the time evolution of this quantum system is. These are the kinds of things where it's necessary, right? You want to know what the probability is, for example. Let's say let's say I have a semiconductor PN junction, right? So what's PN junction? Right, so I have P and N. So I have two different types of material, a P type and an N type, right? And so what happens is this has excess electrons and this has fewer electrons. And then what's going to happen is at this, there's kind of a an area here where they fill in, right? The electrons are able to move over to the into the holes of the P type and fill in some of that area, and so you have this neutral area in between, right? And this is what a semiconductor junction is. And now, if I were to put a potential across this, like a voltage, what's going to happen? I'm making this more negative and I'm making this more positive, right? And so eventually I'll get to the point where there's a breakdown where all of a sudden my electrons have enough energy, they're able to just to leap over this gap and flow, right? So it's the breakdown voltage. Or if I reverse it, right? If I all of a sudden put a positive, right? I switch the voltage like this. Now all the extra electrons are going to flow here, and then these are going to go around in a circle, right? So now what's going to happen is you're going to get very easy current flow, right? These are different. So this is how you do like a gate in a logic gate, right? It's you have these different materials that have different, by doping them, you give different excess electrons or too few electrons, right? But you need to know, hey, how are my electron states going to evolve over time when I put some potential, in this case, literally an electric voltage across it, right? I want to know how the state that's describing the position of this electron is going to change over time. Is it going to move that way or is it not? And let's say my potential is changing over time too, right? I have something like I have I'm going to apply a voltage, but it comes on as a ramp to this other voltage, right? At some certain point, what is my likelihood that I'm going to start getting current jumping across this gap at a certain voltage? I want to know this because I need to design the materials and the voltages I'm applying to this to determine if I'm going to have a transistor that's forward or backwards bias, these sorts of things, right? Is it going to act like an on switch? Am I going to over bias it the wrong way, go into breakdown where all of a sudden current's flowing in the wrong direction? You don't necessarily want that, or maybe you do. There are certain types of diodes that are designed to operate in breakdown, right? So it means you have no voltage until you hit some certain limit, and then all of a sudden you have voltage. Or current, I should say. You have no current until your voltage reaches a certain level, and then all of a sudden you have current. So it gives you kind of a switch. You know exactly when you hit that voltage, that kind of thing. But determining the time evolution of these states, right? These are all quantum processes that are going on here. You need something that'll essentially give you that time evolution operator, right? So this is one way of doing it. Now, I will put this out there that this is not the way that is used in most quantum mechanics, because even though it is mathematically equivalent to what's more commonly used, except under certain niche conditions, this is much harder to solve. So the Feynman path integral method isn't always used, right? But essentially, so if we go back to the idea of what this is actually looking at, right? What this big D here derivative, whatever you want to call it, is looking at, it's looking at essentially the total energy change, right? Because we said we're integrating the Lagrangian, right? So we're looking at the energy change, how the kinetic and potential energy are changing as you move over time in a certain potential, right? That's what you're talking. And then each of these actions, right? Each of these different actions that you're looking at, each of these ones that are being that are in the not the sum, it's the product. They're in this product, right? Each of those is potentially a different way for it to get there, right? So it could go this way, it could go this way, it could go this way. There's a whole bunch of different ways that this electron could potentially move from this state to this state. Now, the states don't have to be positional states. They can be. They don't have to be, right? You could be talking about energy states within an atom. You could be talking about radioactive decay, right? Is my nucleus going to decay for over a certain amount of time, right? And I want to know what that, what the half-life is of that, because it wants to go from this higher energy state to the lower energy state by decaying, but it's got like a barrier to go over before it can get down to that state. So it's got to essentially tunnel through this barrier before it can drop. And that's a random quantum process, right? So that's one reason why they use Q, because Q can be positioned, but it doesn't have to be, right? It can be, again, we're just going through some possible use cases of this, right? So Q, I was just saying Q could be position of electrons in a diode or something like that, right? Or it could be we could be talking about whether or not a radioactive nucleus is going to decay. That's another thing that's a time evolution state thing, right? Or it could be if a photon's going to go through, how a photon's going to propagate through a double slit experiment. Any of these things, any of these sorts of processes you can describe in this way. And so, but taking a step back, what I think is the most interesting about this, to my mind at least, because I'm, again, looking at this for kind of other non-quantum mechanical reasons, is, man, this really is just a transformation the same way we did the Fourier transformation, right? You're really just doing that. And your kernel, as we saw with the other, that sort of like generalized version of the Fourier transform, in that other paper a while ago, you have this kernel, you have some kernel function, right? That's describing the evolution, how things evolve, going from one variable set to the other variable set. And it's doing exactly the same thing. And so this is why you can start to see these analogies to this other aspect. That's why it connects in with the what's it called? Not the Fourier, the ambiguity function stuff that we had looked at before. Because this all falls within that same larger class of functions that the Fourier transform and those other transforms fall into. Okay. So we said we'd find that for an arbitrary metric, GAB, things are unfortunately not so easy. So, so if the space that you're operating in isn't nice and flat and pretty, things get messy. The first formulation for this case is due to DeWitt, and okay, and his result reads, excuse me. So here, let's look again what we have, right? We've got this piece in it. There's the dq, right? There's our square root of g, excuse me, that we'd mentioned before, that sort of dropped out because we said g is just a delta function. So essentially it's just 1, right? So but now g is no longer just 1, so we can't just drop that out. So there's our square root of g there. And now we have this. Interesting. We have this extra term. What's that extra term? What's r? Oh, okay. Oh, so this is like relativistic quantum mechanics. All right. I see what we're doing. Okay. So R is, it's called the Ricci tensor. It's a description of how space is changing. So if you're in one spot, right? Any tensor, think of it like this. If I'm sitting right here, right, and I'm in a field of some sort, say an electric field or a gravitational field, right? Let's say I'm in an electric field and it goes here like this and like this and like this, but over here it goes like this, and then over here it goes like this and 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 like that, right? So it's changing depending on where you're going, right? I need to know if I'm in this position and I look out in each direction, how is it changing in each direction, right? What is the direction and magnitude of my field in each direction? Cool. I can do that. I can set that up. But now I also want to know what's happening here, and I want to know what's happening here, and I want to know what's happening in all the spaces, right? All these possible positions. Now I need more than just a description of the field. I need a tensor that's like a, if you've done anything with vectors, right? So usually a vector is like ax plus by, y, right? And so it's, the vector is telling you how things move, or I'm sorry, right? How things are moving in x and how things are moving in y. But now if you add extra dimensions onto it, that's when you go from a vector to a tensor, right? So a vector is just described by the number of dimensions that you have within it, is the rank of the vector. So typically vectors are just, because they come from classical mechanics, are three-dimensional is the max that you get for vectors, right? X, Y, Z. But then as you start going into adding other things like, say, time onto your vector, you'd have a four-dimensional thing, which is a four-dimensional tensor. Anyway. The point being, R is a tensor, right? That's describing how things are shifting in different directions at each individual space. Okay, so then that is the limit as n goes to infinity. So again, if you remember, we're still splitting things up into little pieces, and then taking the extreme of where the size of those pieces go to 0, right? And the number of them goes to infinity. So this is still our constant here that we had talked about, right? So that's not really affected. Now we have here's our product, right? And we're integrating again. But now our metric here, right? G is no longer just 1, so you have to keep that in the integral. Times, let's see what happened here. Oh, okay, we just expanded, let me see, sum from 1 to, okay, we just expanded out this D, the capital D, right, into our sum and our product. And now we've got so now we're looking at how all the different variables are changing. So if we remembered, the delta was from the initial position to the final position, how it's changing. So it's like QJI or F minus QJI, right? It's the final minus the initial, right? For each of the steps, for each of those steps that you're looking at, right? So again, you're comparing how things are changing over each step, and you have this nasty old Ricci tensor, which I'm not going to go into. Suffice it to say, for the Ricci tensor, you're looking at the curvature minus the scalar curvature. Oh man. Thinking. I have done this before, but it's been a very long time since I've dealt with Christoffel symbols and all that kind of jazz. All you need to know for right now is it's a measure of how the space itself in which you're operating is shaped, right? How it's changing as you go, as you move around your space. How is it change? How is the geometry of that space itself changing? Because again, this could be, for example, physical space. If you're talking about, right, where I've run into this before is with general relativity, you come across the Ricci tensor, and that's physical space, like your XYZ coordinates, warping as you're going around a gravitational object. Oh? Okay. Let's hear news. Yeah. So yeah, I'm sorry. I'm just trying to like go through my head and put together, because I don't fully remember all this stuff. It's been years since I've done it. Okay, no worries. But what's the news? Yeah, so I'm trying to remember some of this. I think the big thing you need to take from this is that you're also taking into account how the space itself through which you're moving is changing, which in like general relativity is because you're in a gravitational field, right? And so space time itself is warping. So what it means to go straight changes because you're moving through a non-Euclidean, non-flat space. But you could also be talking about, right, you don't have to necessarily be talking about a physical space as we think about it as left, right, up, down, right, X, Y, Z space. You could think of it in terms of other, right? It doesn't have to be a physical space. It can just be a degree of freedom, right? So you could be talking about going through different energy or going through, whatever you want to, whatever space you happen to be set up in. You could be moving through a different set of functions, right? Mathematically, they don't care what those dimensions are. It's just a way in which it's just a variable that you can change, right? So, but the way the variable changes depends on the space through which you're changing your variable. What's the good news? Do you have a follow-up? Is there a follow-up? Do you have another one? Set up? Are you setting up another one? Do you have a third date set up? Want to know more? Want to hear good news? Woo! Wow! Well, that's fast. That's good to hear that things are moving along so well. I hope you have a wonderful time with that, and that there are no odd surprises. But congratulations, that's a big step. That is a big step. So I can't wait to hear more as it moves on. Super exciting. I love following this. This is great. I'm just very happy and excited for you, and I hope things continue to go well. But yeah. So so when it comes to this, right? Yeah. I'm super excited. It's great hearing these stories. That's awesome. So yeah. So that's why that's the other thing you're taking into account in this, in this equation is the way in which the space itself is geometrized, right? In addition to how something is moving through that space. Okay. Of course, we identify Q prime as Q naught, Q double prime as Qn. So again, that's our starting and ending positions. In the limit that n approaches infinity, right? So again, we're talking about cutting up our pathway to an infinite different set of possible steps here. Two comments are in order. One, equation 1.7 has a form of equation 1.6, but the corresponding action, right, which we said is the integral of L, and again, L is Ke minus Pe, is not the classical action. Respectively, the Lagrangian L is not the classical Lagrangian, but rather an effective Lagrangian. Right, because now we have... Hi, Potato! Hey! Hi! Oh, did you have fun with that? Oh, thank you. Thank you for looking me in the face. I appreciate that. You're such a good boy. Did you enjoy that? I know you're so happy. It's so good to see you. It's so good to see you, Potato. No, that is not yours, but I'd love to say hi. Hi, Potato. You good boy. Oh, yeah, I know. Where's your toast? Yeah. Yeah. Good boy. He is super excited. Okay. Like, I from Death Note. So I haven't seen, or I've seen like one episode of Death Note, but that was a long time ago. So you'll have to explain the reference a little because I am dumb. Right. So now what we're talking about, right? It's we have to hi. Hey, Bubba, what do you want? Why are you so excited? Why are you so excited? What are you so excited about? I think he wants me to go out with him. L from Death Note. Which one is L? Man, it's been a long time since that. So what they mean by an effective Lagrangian, right, is, again, we're moving through a curved space, right? But what if we flatten this space, right? It's just a coordinate transformation. So if I flatten this into flat space to make it a little easier to deal with, I now just have an extra term I have to take into account. That's the term that comes from this this curvature. So my path might be round like this, right? It might be in orbit, for example. So there's an effective Lagrangian that takes into account how the space itself, if you took this space and you transformed it flat, it's a good question. Unfortunately, Potato cannot go for WALK right now. He is still recovering from a surgery on his leg. And he is not doing a very good job of not jumping around, right? He's supposed to like not jump around and restrict his motion so he doesn't hurt it. He's not doing a good job of that, but so he was just outside, I think, and he got really excited. Anyway. Yeah. He's not very good at that, but it's okay. It looks like he's calmed down a little. He was outside, he got overheated, he got excited, he's jumping around, he had his toy, and so now he's laying down. So he just came in, he needed to tell me what happened, and then he could go and lay down. Anyway, right. So how we deal with this weird geometry is we say, well, that's the equivalent of a flat geometry plus some other change in our path, right? Because we know how to deal with paths. The quantum correction, h bar over 6mr, is indistinguishable in order to derive from the time equation, the Schrödinger equation, the time equation on the Schrödinger equation. The appearance of a quantum correction delta V is very general feature for path integrals defined on curved manifolds. So again, the manifold is the space, right? It's over curved space. But of course, delta V is proportional to h bar squared, depends on the lattice definition. So, right, it depends on how the space is, how quickly your space is changing. A specific lattice definition has been chosen, right? So they chose, if you think of it like this, right, you have a grid of positions that you're talking about. You have to choose how you're determining that grid, right? What's your spacing on the grid? So that's the lattice he's talking about. So Potato had, he has on his other leg too, but so he is a half Beagle, half Basset Hound. And because of that, because of the Basset Hound side, one of his legs, as he was growing, sort of rotated very much past 90 degrees. So it was very awkward, and he was putting weird weight on his knee. So essentially what they had to do was take his leg, cut the bone, rotate his leg forwards, and then put in a bunch of supporting plates and screws and stuff to put it back into position, right? So it's just it's a birth defect. And it's very common in Basset Hounds, but it was like to such an extreme degree that it was causing issues. So they had to literally rotate his leg. Yeah. He was not very happy about it. It's a very extensive surgery. He's still in recovery phase. He's very bad at recovering because he's like, oh, I'm gonna start sprinting again. Like, no, Potato, don't do that. But he's slowly getting better. So he has next week. He has a follow-up appointment. So we'll see how well the leg is healing interior. The exterior is healed, luckily, but we'll have to see how the inside is healing up. Yeah. So, poor Potato. The worst thing is he couldn't go to his, we take him to a place with a whole bunch of other dogs. I'm not going to say the name because he knows the name. That he would play at during the day, like all day. He would go and play there. And he hasn't been able to do that because, again, he jumps around too much. So hopefully he'll be cleared next week to be able to go back and spend time with his friends again, because he is getting increasingly Velcro dog. So in other words, he has to be where one of us are at all times, because his, he was getting used to being a little more independent, but now that we've kind of spent so much time with him and just he hasn't done anything else, he's becoming more and more dependent on us. So we want to, hey, go back and play with your friends again, go and do things independently of us, that sort of thing. Yeah, he'll get better. It's just gonna take a little bit, but these things always do. Yeah, he's been really good about it. But he's just a stinker. He tries his best. He honestly does. So that's one thing I will say. Some dogs, like our last dog that we had, you could see them scheming to get away with things. Potato honestly does try his best to do the right thing. He really does. He just sometimes gets so excited that he gets off course. But he honestly tries. Yeah, so anyway, so all right, so a specific lattice has been chosen, right? So we said the lattice is how we define the space. The metric terms in the action are evaluated at the pre-point qj minus 1. So imagine you go backwards a step from 0, changing the lattice definition, i.e. the valuation of the metric terms at other points. For example, the post point, the midpoint. Hold on one sec. Let me just read this real fast to try and understand it, and I'll sort of try and explain it. How the metric at other points, for example, the post point or the midpoint, changes delta V because the Taylor expansion of the relevant term, all terms O of epsilon contribute to the path integral. This fact is particularly important in the expansion of the kinetic term in Lagrangian, where we have... Okay. So changing the lattice definition, for example, the evaluation of the metric in terms of other points. So how one point is what the curvature of things look around one point, right? So if my space is doing something weird and I'm at one point, how do things look like from that point compared to a point over here, right? What do things look like? So so when you change the lattice definition, for example, the evaluate, that changes the potential delta V, right? So again, we're pretending that we're taking this, how the space is shaped, and we're saying it's equivalent to just some potential, like a gravitational potential or something like that, right? And we're just calling that potential delta V. But if you change your definition of how you're measuring this, your metric, right, that it's going to change what delta V you're going to use. Since the Taylor expansion, which is saying how things are changing, and in a Taylor expansion, all terms of order epsilon contribute to the path integral, right? So, as you change that lattice, right, which is changing how you're cutting up the space, all of those different terms are important. So, okay. I'm not 100% understanding all of this, but what I'm getting out of this is as follows. This first statement. So you have to choose your measure, essentially, right, of how you're going to measure your space, what your specific lattice is that you're using to measure your space, because that's going to change your effective potential that you're putting in there to take into account the changing of the space, which kind of makes sense. If you think about it for a second, let's think about this for a hot minute. Right? If I have some space that is moving, and it's moving in weird ways. So I'm just going to do this think of this as a one-dimensional space, right? That's moving like this. And I have a ball that's theoretically moving across the space, right? It's going down, it's going up, going down, right? I'm trying to figure out how this ball is moving. If my metric is has a certain spacing, or essentially my measurement has a certain spacing, the lattice that I'm choosing has a certain spacing, I'm going to miss small things like this, right? I'm going to miss those small little perturbations. So if I'm then saying, well, what happens if I converted this line into a flat line, and now I looked at how the ball was moving on this flat line, all of a sudden the ball would look like it's going slower, then faster, then slower, then faster, then slower, then faster, right? That's what it looks like if I make this straight. I have to change how I'm describing the motion of the ball in terms of this janky up and down. But if my depending on the spacing determines what goes into that, right? So that's determining what I actually see. And so what goes into my description of how the ball is moving in a weird, janky way. I think that's probably the best way. Actually, think about it. That's the best way to think of this, right? This one-dimensional space. This is what my metric is actually doing, right? My metric is telling me how the space itself over which I'm moving is converting into the apparent motion of the ball, right? So the ball is going, it's got to go up the hill, so it's going slower. Hey, Toasty, good to see you. So this is how a space changes the motion within that space, right? It feels like it's going uphill, so it's going slower, and then it's going downhill, so it's going faster, and it's going uphill, and it's going downhill. So if in this space my ball is moving at a constant velocity, that means if I were to flatten out all of these into an equivalent straight line, it couldn't be moving at a constant velocity. It's moving at it's going slower than faster and slower than faster, right? It's doing all these weird things. So that's why the lattice that you choose to describe the space matters. Hold on. Wait. I can do this. Hold on. Wait. I can respond. I can respond. Hold on. Toasty is on vacation at a lake. Great time at the lake. Toasty's awesome. Toasty is another streamer. Doesn't do math stuff, but she's really nice, awesome person, and definitely worth supporting. But anyway, more of a classical kind of streamer. She streams a lot of space games. She really likes that. So you can find her also, Toasty Morsel, on YouTube as well. Can I do a shout? I've never done a shout out before. Let me test this. Is it backslash? No, / shout out Toasty Morsel. Yeah, there we go. So yes, great person, great streamer, does cool stuff. Anyway, I just wanted to throw it out there. Any rate, so yeah, I hope that analogy somewhat made, or that description somewhat made sense of why the geometry of your space matters. And to go back to another analogy to or to go back to another point from our Fourier analysis stuff, if you remember all that jazz, right? Your what frequencies you can see in a signal depends on your spacing of your what's it called? Your sampling rate, right? So your sampling rate is the equivalent of a lattice, and that's determining what details you can see, right? So you have to have, you can generally see things that are lambda over 2, right, of your spacing. So you have to have at least 2 samples per wavelength to be able to see things at that frequency. So the more you sample, the more accurate the more higher frequencies you can see, the more accurate your description of what's going on. Same thing is happening here, but instead of talking about samples of an of a radio signal or something, you're talking about how you're describing a space. Same idea, or a parallel idea, but that's coming in a very different way. But again, you can see how all of these mathematical parallels are going to hopefully allow us to take this methodology into the realm of electronics and signals, which is our ultimate goal, right? That's really what we want to do. We want to look at how this is operating and see, okay, how does that operate in this other field? So what we'll do is we will go down to this theorem and then we'll call it for the mathy today, right? We're not going to get into the proof, but we'll go through the theorem. Okay. One of the basics requirements of the construction of the path integral is Trotter's product formula. Obviously, we have a product going on. Discussions and proof can be found in many textbooks on functional integration and functional analysis, and these are different examples, right? So let's notice a simple proof, right? Let A and B be self-adjoint operators. So we had discussed self-adjointness. It's just a very well-behaved type of operator. So again, an operator can either be described as an integral, as we saw up here, or as a matrix. On a separable Hilbert space. So separable, in other words, you can take f of x and y as f of x. Let me move over here. Times g of y. If you can do this, you can't always do this, but if you can do this, it's said to be separable, right? You take this big function and you can degrade it as a set of smaller functions of individual variables. So you're able to separate out those variables. On a Hilbert space, so that A plus B is defined as dA ... dB. Defined on, I'm sorry. So that A plus B is defined essentially, right? It's defined in the space, right? So in other words, addition is something that makes sense within the space. Then e to the it A plus B is equal to, what is the S limit? Let's see. I'm not sure what this S-lim is. I have to look that up. But essentially, it's the limit as n approaches infinity of e to the I an times bn over n. So in other words, what this is saying is that you can separate out this. Oops. Right. So you can, in other words, you can separate out some exponential that has two operators into two exponentials that have one operator, right? And we're taking this limit on n. So that's useful because, okay. So yeah. So that's what this mathematical operation is saying. So in other words, it allows you to break apart a set of operators in this way. That's all you need to know, right? This is actually like directly analogous to if you actually had just normal functions, right? So if I had e to the a plus b, where a and b are just numbers or variables, that is equal to e to the a times e to the b. This is generally true, right? So in other words, all this is saying is there is an analogy to this in these operators. That's it. It's a little bit different. It's a little bit more complex, but there is a direct analogy to where you can break this up into these things. By the way, logs and exponentials are hugely useful. Anytime you're trying to solve thing where it's like, you know, x to the 4th equals 6x squared, right? And you want to know, like, how do you solve this? So you just log both sides, right? If I take the log of both sides, it's 4 ln x equals ln 6 or I'm just gonna remove the 6. I think it's just 6 ln whatever. I'm just gonna equals 2 ln x, right? So then I can literally just subtract it off, right? And I get, you know, it's a lot easier to solve. Or I divide it out rather, right? So then I get 2. Then I just take the exponential again. Anyway, natural logs are very helpful. Basic, what is a log? A logarithm is an exponent. So that is actually a very useful term to remember. Just I found this infinitely useful. Is we're just reciting this as a mantra. A log is an exponent. So if I say x, or here, 2 to the 4 equals, what is it? 2 to the 4, 8, 16, 30, what, 32? 2 to the 4 equals 32, right? Then that means that log, oopsies, base 2 of 32 is 4. So 4 is the exponent of, here. 4 is the exponent of 2 to give you 32. That's what a log is, right? So typically, right, you'll initially see it as base 10, right? So it'll be like 10 squared is 100. So log base 10 of 100 is 2, right? So typically log without anything like that is going to be base 10. Natural log is log base e, right? So if I said, and it's natural because e comes up in so many different ways and does all these kinds of weird things, right? It's part of the integral derivative stuff, right? The integral, right? The integral of e to the x is e to the x. That's right. It's an important identity. So exponentials happen a lot. So if I were to take, so if e to the x equals 3, right? Then natural log of 3 is x, which is, right? So that's all it's doing, right? That's, the log is the exponent of e. So again, natural log means log base e of 3, right? But if you notice, this has a very helpful property of how would I solve e to the x equals e squared? No. 1 is anyway, log of 1 is always 0 because any number to the 0 equals 1. Right? So look, let's say I have this, right? How do I solve this? Well, the easiest way to solve it is, let's take the log of both sides, right? If I take the natural log of this side and I take the natural log of this side, then I have hey, look, I have x times ln of e, which this is 1, equals 2 ln of e. This is 1. So I know x equals 2. Obviously, I could just like look at this and say, well, x is clearly 2, right? But this is the way to prove that x would equal 2, right? Because if you take the log, your exponent comes out, right? And so now you have this great, easy way to do it. That's why logarithms can be really useful in when you start running into complicated problems, right? You start running into things where you start running into issues. Sometimes taking an exponential or taking a logarithm can help you because it allows you to do things like manipulate what's in your exponent, which is essentially what we're doing here, right? We're going from an exponent that's a sum of these two, of a and b, to an exponent that's just a function of a and an exponent that's just a function of b. Why is this useful? Let's take a look at this. Why this would be useful. Let's say I want to integrate e to the a plus b with respect to a. That is not the simplest thing in the world at first glance, right? Because e is a function of a and b, so you can't directly do it, right? Well, if you split it up, right? And so if I have I want to know e to the integral of e to the a times e to the b dA. Well, with respect to a, e to the b is just a constant. So I can literally just go bloop and pull that constant outside because it doesn't vary with respect to a. It doesn't care what a is. So now I have e to the b times the integral of e to the a dA. And this I can do. So these identities that allow you to manipulate the exponents can be very, very helpful. So that's why he's going through this. In this case, a is not just a variable, right? Now a is this nasty tensor operator matrix thing. But he's saying that, hey, look, you can do the same kinds of manipulation of this weird tensor operator matrix thing in an exponent that you could do with normal exponents, right? So that is the importance of this that allows you to start moving things around. Where again, remember we had the sum that we're integrating over of all these things in the exponential and all this like crazy shenanigans that we saw. Look at all this crazy stuff that's going on. We have an exponent, of a sum over all j's of all these different variables. Well, what this says is that, hey, there's a way that we can split this off into, say, a multiplication of different exponentials of single variables, right? Of each of these j's. So now I can start you can see how they're going to eventually attack this. Now I can start separating apart this weird, crazy exponential set into something that might be more manageable. Emphasis on might. Right? But that's kind of the process that they're going through on some of this stuff. So hopefully that sort of makes sense. Again, as with all of this stuff, I don't understand all of what's going on. I'm trying to pick out bits and pieces as I go through. I'm trying to make connections to analogies to different types of math or different types of things as I go through this. Some successfully, some less successfully. Sometimes I look at stuff, I'm like, I have no idea what's going on. And so the goal is to, again, go through this and slowly gain an understanding and a knowledge of these things as we move through them. So, thank you for showing up to my birthday math. What is I have to see if someone's still online. Hold on. Hold on, because I do want to raid them if they are still online. 1 second, just looking something up really quickly. Yeah, they are. Cool. We are going to raid an artist by the name of Buelty. And he is a very good artist. He's the one who made we've raided them before. He's the one who made this and this, and where's my other one? Why did I not? Where's my other one? Where's my heart emoji? What the poo? Well, these two and then the heart emoji. Buelty made those. So I'm going to go ahead and raid Buelty. I may be back on later to do some other silly things just for funsies, but I did want to do this. At least melt our brain with a little math as a birthday present to all of us. So, with that out of the way, thank you again. Look forward not this coming week, the week after. We're gonna try doing that charity stream. We'll see how it works. No clue. That is the wrong one. BEAULTEA. So yeah. Look forward thank you. Have a good day, and Sunday we'll be back for our Sunday morning papers. We're going to continue our philosophy paper next time. In the meantime, the raid will move forward. It's Mathy Math time. I hope you enjoy some art. I believe he is working on his comic that he does, which is really cool. Who does that? Anyway, so thank you again, and away we go.